Today we're going to discuss a specific type of wave phenomenon, and that is known as sound. Sound is a disturbance of matter that is transmitted from its source outward. When this tree fell some time ago, the atoms of air were disturbed. Physicists would call this disturbance sound, whether or not someone was around to hear it. Hearing, on the other hand, is the perception of sound by the organ that is used to perceive those disturbances. In most cases, that organ is called an ear. This glass was shattered by a high-intensity sound wave of the same frequency as the resonant frequency of the glass. That's why the glass shatters. When the sound is not visible, the effects of sound prove its existence. When a string is plucked on an instrument or in some other situation, it moves from right to left, and the vibrating string moving to the right in this diagram compresses the air in front of it, while at the same time it expands the air behind it. The compression is, as it says, called compression. The expansion is called rarefaction. As the string moves to the left, it creates another compression and rarefaction in the opposite direction as the initial compression and rarefaction. After many vibrations, there are a series of these compressions and rarefactions that move out from the string, and this series is known as a sound wave. The graph shows the gauge pressure versus the distance from the source. Pressures vary only slightly from atmospheric pressure during normal or ordinary sounds. Sound wave compressions and rarefactions travel up the ear canal and force the eardrum to vibrate. There is a net force on the eardrum since the sound wave pressures differ from the atmospheric pressure that is found behind the eardrum. A complicated mechanism of vibrations in the bones of the middle ear and then subsequently in the fluid in the cochlea in the inner ear convert the physical vibrations that the sound wave induced to nerve impulses. And this is then perceived by the individual. When a firework explodes, the light energy is perceived long before the sound energy arrives. Sound travels much more slowly than light. Another difference between sound and light is the fact that sound is a mechanical wave. That is, it requires a medium in order to pass along or to move along. Light, on the other hand, is an electromagnetic wave that does not require a medium. Therefore, sound does not travel or is not emitted in a vacuum, whereas light travels in a vacuum. Sound waves emanate from a source vibrating at a particular frequency, F. They propagate at a velocity, VW, and have a wavelength, lambda. These are related to each other with the following formula. The velocity of the wave, the sound wave, is equal to the frequency of the sound wave times its wavelength. The velocity of sound is affected by temperature. At 0 degrees centigrade, the velocity of sound is 331 meters per second. And this formula, which you should keep and understand and have available to do your problems, converts any velocity to a new velocity based on the temperature, ambient temperature. The T in this case has to be converted to Kelvin in order to be applicable or used in this formula. Now, what is actually being affected is the molecules that are in the gas with which the sound travels, or in the medium with which the sound travels. And so the velocity is that's actually being looked at is the average velocity of the molecules in the medium. And this can be calculated using the following formula. In this case, the small case k is something known as the Boltzmann's constant, which is a function of whatever the gas is made up of. That is to say, helium would have a different Boltzmann's constant than hydrogen, which would have a different Boltzmann's constant than air. M is the mass of the gas particles. So the medium itself is important both in its ability to move as well as in the size of the particles in the medium. A bat, shown in this picture, uses sound waves in order to locate its prey. This process is known as echolocation. It can calculate the time, using the time it takes for the echo to return to it after it's emitted its sound. It can calculate the distance to the prey. Now, in a single situation, the velocity of the sound that's emitted is the same. Therefore, as shown in this diagram, if the lower speaker, called the woofer, emits a low frequency sound, a lower that's detected or heard as a bass sound, it must have a larger wavelength in order for the velocity formula to work out. Similarly, the higher frequency sound, known as a tweeter, emits a higher frequency, which is heard as a higher frequency, the treble part of the music, and it has to have a smaller wavelength, again, to obey the laws of velocity. So, for this situation, let's calculate the velocity of the sound waves, the wavelengths of the sound waves at the extremes of the audible range. The audible range is anywhere from 20 hertz, which is extreme bass, to 20,000 hertz, which is significant treble, with an air temperature of 30 degrees C. Assume that the frequency values are accurate to two significant figures. So let's take a look at how we would do this problem to calculate this. The first thing we would have to do, obviously, is we would have to calculate the new velocity of sound, because it's at 30 degrees. The formula again was 331 times the square root of the temperature in Kelvin divided by 273. In this case, it's going to be 331 times the square root. 30 plus 273 is 303 divided by 273. And if we do this calculation, we get a velocity of 348, and that's meters per second. So the velocity is 348 meters per second. Now, V is equal to F lambda. Therefore, lambda is equal to V divided by F. So, we have two calculations here, 348 divided by 20 and 348 divided by 20,000. So the wavelength up here is going to be 17.4 meters, and the wavelength here is going to be 1.74 times 10 to the minus 4 meters. I'm sorry, minus 2 meters. 1.74 times 10 to the minus 2 meters. Let's take a look at a couple more problems. Air temperature in the Sahara Desert can reach 56 degrees centigrade, or about 134 degrees Fahrenheit. What is the speed of sound in that temperature? This again will use the same formula we used before. V is equal to 331 times the square root of T over 273. And this is going to now be 331 times the square root of 56 plus 273, which is going to be 329 divided by 273, and that's going to equal 1.098 times 331, which is equal to 363.4 meters per second. A sonar echo returns to a submarine 1.2 seconds after being emitted. What is the distance to the object creating the echo, assuming that the submarine is in the ocean and not in fresh water? Now, in order to do this problem, I had to look up the velocity of sound in seawater, and it's 1,540 meters per second. You have to have that in order to do this problem. And we know that distance is equal to velocity times time, and the time is going to be 1/2 of 1.2. So that distance is now going to be 1,540 times 0.6, or 924 meters. Now, moving from these simple calculations of frequency, wavelength, and velocity, let's move on to something a little bit more complex, and that is the evaluation of intensity and loudness. You will recall that intensity is equal to the power divided by the area. This shows a roadway in India, which is a very loud and causes things to be very difficult to hear. But again, intensity is equal to power, capital P, divided by the area, A. And we talked about that in the last couple of lectures. Now, converting this to sound, we use a formula that looks like this, and you've heard of dBs. That stands for decibels. The BEL being the BEL being the fundamental unit of sound. And this calculation was used in order to convert this to decibels. And I0 here is a standard number for intensity, 1 times 10 to the minus 12 watts per meter squared. I is the intensity of the sound that's being emitted. Log to the base 10, you understand. Now, another way to do this, or another way to calculate intensity, is to look at the change in the pressure that's caused by the sound wave. That change squared divided by 2 times the density of the medium times the velocity of sound. So there are two ways to calculate it. One uses the more mechanical approach, looking at the pressure variation that's caused by the sound wave, and the other uses a standard in order to convert this to something related to the standard. Now, this graph shows the effect of this formula on sound waves. For example, you look at a pressure gauge, this graph is a pressure gauge looking at the change in pressure based on two different emitted intensities. And because the change in pressure is squared, you see that a medium change in pressure causes an enormous change in the intensity. And the more intense the sound is produced by the source, the larger the amplitude of the oscillations. Because this higher pressure, it exerts larger forces on its objects that it encounters. And for example, I don't know if you remember, but if you saw the movie The Hulk, the second version with Ed Norton, they used a sound emitting cannon in order to try to capture him. And this sound emitting cannon, the force that was generated by this sound emitting cannon was quite remarkable. Now let's take a look at a couple problems with this. The first one is calculate the sound level intensity in decibels for a wave traveling in air at 0 degrees centigrade, having a pressure amplitude of 6 0.656. Okay, so let's take a look at how we would do this. You will recall that this formula for intensity was the square of the change in pressure divided by 2 times the density of the medium times the velocity. So in other words, fortunately this is 0, and so the velocity we now know is going to be 331 meters per second. The change in pressure is given as 0.656, and I had to look up the density of air, and it's 1.225 kilograms per meters cubed, which is and so if we put this into this formula, we get 0.656 squared divided by 2 times 1.225 times 331, and that equals 5.21 times 10 to the minus 4 watts per meter squared. Now to convert this, we have to use the other formula. Beta is equal to 10 log base 10 I over I0. And so that's going to be 10 log, I'm just going to say log for log base 10 now, and it's going to be 5.2 times 10 to the 4 minus 4 divided by 1 times 10 to the minus 12. The second problem states that what is the intensity of sound that has a level 7 decibels lower than 4 times 10 to the minus 9, and then 3 decibels higher than the same intensity. So obviously, in order to do this, first we have to see what the decibel level is for the given amount. So what is the intensity level for 4 times 10 to the minus 9 over 1 times 10 to the minus 12? And if we look at that, we get 36 decibels. Now, the first one's going to be 7 less than that, so 29 decibels. And the other one's going to be 3 more than that, so 39 decibels. So in order to do the first one, 29 is equal to 10 log 10 of some intensity we don't know yet over 1 times 10 to the minus 12. So that means if you divide both sides by 10, that 2.9 is equal to log 10 of I over 1 times 10 to the 10 minus 12, excuse me. If you take the anti-log of this, you get 794, and then you would multiply it by this number, 1 times 10 to the minus 12, and that's going to give you the new intensity. And the new intensity here is going to be 7.94 times 10 to the minus 10. The other one is similarly done, 39 now, log 10 I over 1 times 10 to the 12 minus 12. So this is going to be 3.9 is equal to log 10 I over 1 times 10 to the minus 12. And if you do the math here, you basically get the same 7.94 times 10 to the, now it's minus 9 instead of minus 10. So here's the answer to these three problems. And we'll stop here and start with a discussion of the Doppler effect when we return.